Welcome, everyone. It's my pleasure to introduce Anne, who's going to be telling us about a series of simple affine VOAs at non-admissible levels arising from rank 1 4D superconformal field theories. Thank you, Anne.
Yeah, thank you very much for the invitation. I'm sorry for the long title first, and also for the changing the time for me. So indeed, today I would like to talk about joint work with Tomoyuki Arakawa, Suhang Dai, Justine Fasquelle, and Bohan Lee on indeed a series of simple affine VOAs that come from physics in the context of the 4D 2D duality. So this is a reference of the preprint. So let me explain a little bit more on what I want to talk about. So please interrupt me in case you need some question. So more precisely, in the talk, I will be interested in the representation theory and associated varieties of the following series of vertex algebra. So aim represent, I will be interested in the representation theory and associated varieties of the following simple affine vertex algebras. So I will explain the notation. The first one is this one. The second is the simple one associated to B3 with the same level -2, and the last one is this one. So can you see? Yeah. Okay. So where you can guess the notation. So maybe I don't enlarge so that you can see the whole screen. Yeah, that's better. So where you can guess the notation for K, a complex number, and G, a simple Lie algebra. This is a simple quotient of the universal affine vertex algebras associated with G as level K. Okay, is it okay? So I am interested in this series where the level is -2 and the simple Lie algebras are G2, B3, and D4. So first of all, so let me reduce a little bit the size. Yes. So first of all, this is indeed a series. So first of all, we have indeed embedding between these two simple vertex algebras, and this is due to a nice result of Adamovich and Perche in 2013, if I am correct. And I will go back to these embeddings, but this is in fact conformal embeddings. But let me precise later. Okay, so first of all, I would like to first explain how we can obtain this series a bit more precisely. Second, I will explain the main results we have about these series of simple affine vertex algebras. And third, I would like to first motivate why it is interesting to focus on these special series. And then I will discuss maybe in more details some ideas of proofs. So first of all, let me explain in more details how we get these embeddings. So I start with a classical setting about the embeddings between G2, B3, and D4. So let's start with the simple Lie algebra D4 with Dynkin diagram. I guess you all know this. And as you know, the group of Dynkin automorphism of D4 is a symmetric group of order 3, all right? And it is well known that the invariant Lie algebra is isomorphic to G2, all right? So first of all, you have an embedding of G2 inside D4. And moreover, if you consider a 2-order element in S3, so any transpose in your symmetric group, and then you consider the group generated by tau, so this is just the cyclic group of order 2, then it is known that the invariant part of D4 through this group is isomorphic to B3. So in this way, you get, first of all, embedding at the level of Lie algebras between G2 and B3, and between B3 and D4. This is not a Levy subalgebras, but we have these embeddings. All right. So obviously, these embeddings induce embeddings at the level of universal vertex algebras. So this induce, for any level, embeddings at the level of the universal. But in general, this does not pass through the quotient. So the result of Adamovich and Perche is remarkable because at the precise specific level -2, we have conformal embeddings. So first of all, -2 is not critical. So these algebra are vertex operators algebra. They are conformal vertex algebras. Any question?
I think someone had their mic not muted. Yeah.
Okay,
thanks.
sorry.
Yeah.
So in general, it does not pass through the quotient. Through the simple quotient. But remarkably, so now I just repeat, but it's a bit more explicit. Remarkably, for k is equal to -2, we have conformal embedding. So conformal just mean that the conformal vectors is the same. Conformal vectors are the same. So let me rewrite the series.
And Anne, for the other levels, even at the universal embeddings, the conformal vectors are not the same?
No, I don't think so. No, I don't think so. Yeah.
Thanks.
Okay, so now I would like to precise. So first of all, it's not only embedding, it's conformal embeddings. Second, it's a bit more precise because in fact, this is precisely the invariant part of the simple quotient associated with D4 through the action of S3. The action of S3, S3 also acts on the universal vertex algebras, and the key point is that it acts on the maximal ideals in this case. And this is precisely the invariant part through the action of tau. And moreover, so this is also interesting. And last interesting remark is that in fact we have finite extension. So this is in fact a finite extension of minus the simple affine vertex algebra associated to B3, sorry. So I mean by that as a module over L-2 of B3, we have finitely many modules in this decomposition. And similarly, this one is a finite extension of the first one. And in fact, the last one is a finite extension of L-2 of G2. Okay, so this is a picture. And it turns out that these vertex algebras are very, very interesting. First of all, from the physical point of view, I will try to explain. And second, the result I will present now it's a very nice examples for many conjectures in the mathematical settings. So, so let me first explain our main results, and then I give some motivations. So as I mentioned, our result is first of all about representation theory and associated varieties. So yeah, let me comment the main result. So it's about representation theory in the category of these three vertex algebras, but in fact, the case of Z1 associated with with D4 was done in our previous work with Arakawa before. And second problem we were interested in is about the associated varieties of these vertex algebras. And here, the case of Z1 associated with B3 and Z1 associated with D4 were also done in our previous work with Arakawa. So for the associated varieties, the new result is about G2. So it's easier to start with associated variety to explain the result. So to state our main result, again, I would like to go back to the classical setting. So I remind you that, first of all, what is the associated variety? So first of all, I recall that to any vertex algebra V, one attach in a canonical way a certain affine scheme, so affine reduced scheme, so let's say affine variety, which is in fact Poisson. And maybe I can detail, this is the reduced scheme corresponding to the zoo C2 algebras. And what is RV? This is the zoo C2 algebra, and this is defined as a certain quotient of V. So where C2V is the span over C of these elements, where I denote as usual the series associated with A in V as follows. Okay, and it turns out that RV is naturally a Poisson algebra. So this is a general setting. And this is what we want to compute in our case. So now let's go back to classical things to explain our results. So let me recall the embedding like this. So I remind you that this is just obtained as an invariant subalgebra of D4. And now this embedding induced, taking the dual, a projection between the dual of D4 onto the dual of G2. All right. But now identifying this dual with D4 through the killing form of D4, now I can also identify with G2 using the killing form of G2. So in fact, I have a projection from D4 to G2. All right. And there is a result by Levasseur and Smith. So not recent. Yeah. Which says that now the image through this projection of the minimal nilpotent orbit in D4. So this is the minimal nilpotent orbit in D4. So its dimension is 10. All right. Is exactly the closure. Sorry, it's the image of the closure of this. This is exactly the closure in G2 of the subregular one. So this is a sub-regular nilpotent orbit in G2, which is also of dimension 10. So this is not so easy to prove, but in other words, this subregular nilpotent orbit is the orbifold of the minimal closure by the symmetric group. Okay. So this is one remark, okay? What is the connection with associated varieties? The connection is that the minimal nilpotent orbit of D4 is known to be precisely the associated variety of L-2 of D4. This is our result with Arakawa. So by our result of Arakawa, the associated varieties of this one is precisely the minimal one, all right? In fact, it is part of a more general result about the Deligne exceptional series. But this is a particular case of this series. So we have this result. And now, because of the result of Adamovich-Persay and other things I will mention after, it's very natural to expect that the associated varieties of for G2 is exactly the subregular of G2 for its closure. So this is our first result. So this is the first result. Oh, sorry. I want to comment. So this is the joint paper. Okay, so the first result is that the associated variety in this series for G2 is the subregular one, the closure. So what about B3? So B3, so is it okay? So this is one thing I want to comment after. So in other words, maybe I should add something. In other words, this is, I would like to write like this. This is one way to see it. This is this. Okay, or another way to say is that it is the orbifold of this one through the action of S3. This is all right. So what about B3? So this was done in a previous work I had mentioned. So let me recall our result. So here again, I would like to start with this embedding. So similarly as before, this induces a projection from, so let's call it now B3. And maybe I should have denoted pi 3 and pi 2, the previous one. So you have a projection like this, similarly to before. And here, again by Levasseur and Smith, the image of the minimal nilpotent orbit closure is, in fact, the unique nilpotent orbit of dimension, the closure of the unique nilpotent orbit of dimension 10 in B3. So in fact, it is a unique short nilpotent orbit. So unique short nilpotent orbit in B3, also dimension 10. So short means that you have a decomposition of your Lie algebra. You have also only 3 pieces if you use an SL2 triple. Maybe it's not so important to explain this. No. So short means it's short in some sense, but it's not so important. It's a unique associated with of dimension 10, and if you prefer, in terms of partition, it corresponds to this one. So if you think of B3 as SO7. All right. And then indeed, the associated variety of L-2 of B3 is this one. So this is our result with Arakawa. So it's L-2 for B3. It's a closure of this. So similarly, you can interpret as orbifold. It's exactly the same kind of picture. So this, oh, sorry. You can also write as the variety of this. Yeah, if you like. All right. So this is a first result about associated varieties. I will try to comment the motivation for that. And about representation theory, let me state our main results. Any questions so far? Okay. So about representation theory, the result as so what we get is a complete classification of the simple module over this vertex algebra and the category O. And as I said, the new part is for B3 and G2. D4 was done in our previous work. So to summarize, it's a complete classification of the simple highest weight L2 minus G modules for G is equal to G2 B3 plus ordinary one. Okay, but this is maybe I recall what does that mean, ordinary here. This means that L0, so the conformal vectors act semi-simply, plus each L0 component is finite dimensional, plus bounded from below, the grading.
And could you zoom out a little bit? Because
yeah,
it's a,
sorry.
yes, thank you.
Yeah, maybe. Yeah. So this is our work. So let me state slightly more precisely what we get. So about G2, I can write the statement like this. So the list, yeah, maybe I write like this, L minus 2, no, sorry. So, okay, so first of all, this is my notation for highest weight representation of the Kac-Moody, the corresponding affine Kac-Moody Lie algebra associated with G2 with highest weight minus 2 gamma 0, lambda 0, where lambda 0 corresponding to K. So maybe, sorry, I should have introduced the notation before, but if I introduce the affine Kac-Moody like this, and also the extended one. So first of all, L0 is just minus D. And now I consider Cartan subalgebra here. And in my notation, this is a weight in duality with K, and maybe later I will need of Z1 with T. This is my notation. So, okay, so you have some highest weight highest weight module, and okay, you have a certain number. It's not interesting. I decide which one. So mu I are explicitly described. Explicit is the complete list of such a module. Okay, and among them, the ordinary one as the following. So you have, of course, this one, because in my notation, this one is nothing but the usual one. And you have two others. Okay, so let me explain a little bit the meaning of this. So we have a complete list of highest weight module. I will say a few words of how we can compute this. So we have 20 such highest weight irreducible module in the category O. And among them, the ordinary are easy to detect because in particular, it must be the top component must be finite dimensional for G2. So you need to have a dominant weight for G2 here. Dominant integrable weight. Sorry, I write better. For only 3 are ordinary. So this is the first, and we have similar for B3, and we had similar for D4. Huh? So maybe, is it okay? Any question about this statement? All right. And so I will state.
I have a question. Maybe is the only condition that's violated for the other weights is that the conformal weight pieces are infinite dimensional?
So what I am saying is that so your question is about how to detect ordinary from the others?
Well, are the others not ordinary because they have infinite dimensional conformal weight spaces?
Precisely.
But they could be relaxed size weights, for instance.
So in fact, I will comment a little bit the proof later. So because I should have stated this later, but anyway. So
okay, thanks.
So there is a way to detect what are the possible weights, and in fact, it's exactly a condition. So I will mention, but you have a criterion. And now you have a classification. So in this theorem, the real interesting part is the first part. All right. And now you want to detect among them which one are ordinary among them. And to see that, as I said, you know that the top component correspond to in fact, the projection on the carton. So if you want it's finite dimensional, you know that this module in particular should be a finite dimensional for G2. But this, we know that they are exactly when it's dominant integral. And because I haven't said what is mu I, but you will see from the shape of mu I that all the other are minus something, or they are not like this. So I have the table. I think it's negative or even not. Either it's not dominant or it's not integral, but you have the table. So as I said, it is explicit. So it's enough to just look at. So similar for B3. Similar for B3. So maybe just I can just say that we have here 13. Well, it's not so interesting, but what is interesting, again, explicit. And here, among them, so you have only 2 ordinary. So the usual one, so which is just a simple quotient, and this one. So these are interesting because they appear in the decomposition of Adamovich pair shape. So, all right. So this is essentially the 3 results. At the end of the talk, if time allows, I will mention another corollary, but this is essentially our work. And so I will go back to the idea of the proof, but the idea is first of all to find singular vector for G2. And here, contrary to what we did for B3 and D4, using works of Perchet, in particular for D4, here the singular vector is very hard to find. It's not in conformal weight, small conformal weight. So this is the first technical part. And also we use a notion of sub-singular vectors. So this is relatively new. And another ingredient, which is not completely new, is to use the W algebras. associated with subregular for G2 in particular. So this is what I will explain. But first of all, maybe to close this long introduction, I would like to give some motivations from physics, because my title suggests it's interesting for physics, and from mathematics. So let me now give some motivation. So motivation from physics. So the first observation is that for expert, you notice that this level is not rational, but slightly more expert, you also notice is not admissible. So it's quite exotic example. So maybe I just write this for G is equal to G2, B3, and D4 is neither rational, just because K is not a non-negative integer, or least. So least means the associated variety is just a point. So here it's not, because the associated variety is a closure of non-trivial orbits. So it's clearly not least. So it's not related in any sense to with rational conformal field theory. So these vertex algebras are not related in any sense to rational field, conformal field theories. But they do appear in higher dimensional superconformal field theories. So, but they do. They do appear in higher superconformal field theories through the 4D to D duality. So I guess some of you already heard about this. So let me just say a few words, and I want to explain, sorry, yeah, it's better like this. So I want to explain more precisely in which context it appears in this setting. So I remind that we have to any four-dimensional is equal to 2 superconformal field theories, so something in higher dimension, what can associate, so let's say ball X, the map, two-dimensional conformal theories, so that is to say VOA or vertex algebras. So this is due to a group of physicists. And the idea is that you can read some observable in physics from a mathematical invariant from the vertex algebra setting. So in particular, this map is designed so that a certain invariant called the Schur index correspond to the normal, of theories. Okay, if you pick a theories here, and then I denote by xt the corresponding vertex algebras, this should correspond to the normalized characters of the corresponding VOA. So I remind you that this is a certain normalization of the characters. Yeah, okay. And conjecturally, you can also read another more geometrical invariant, which is the Higgs branch. So this is a conjecture of Beam and Rastelli, who are part of the group of physicists who constructed this map. The Higgs branch, oops, sorry, correspond to the reduced further associated varieties corresponding to that. So this is a conjecture. And this was proved by Arakawa for a special class of such four-dimensional superconformal field theories called the classes. And the vertex algebras L-2 of D4 is part of this conjecture. But the two others are not. They are not from the classes, but they are part of this story for another interesting class of such theories. So there are other invariants, such as the Coulomb branch, for instance, which are also interesting, and that will be interesting to understand through certain mathematical invariant of the vertex algebras. So now, on the other hand, invariant of the vertex algebras produce a new physical invariant. So remark, the representation theory of the VOAs appearing in this setting should produce new physical invariant. So from physics viewpoint, once you detect a vertex algebra in this setting, it's interesting to study a representation theory. So that is to say, observable, if this would prefer. Of the original superconformal theories. So I have no idea exactly which physical observable it gives, but in a group, Dai and Lee are physicists, and they work a lot about this, and they know what are the motivations. But another thing I want to explain now is that a new advancement since about 10 years in this story is that we can detect, I don't know how to say if it is really construct or detect, a large class of vertex algebras, but no, not vertex algebras, four-dimensional superconformal theories using geometrical methods. More precisely, they have a way to classify all such four-dimensional superconformal field theories whose Coulomb branch has small dimension, and they call it the rank. So let me summarize by saying that there is a classification, new things. So it's not really new, but okay, good things. There is a classification of n is equal to 2, rank 1. So what does that mean, rank 1? It means that the dimension of the corresponding Coulomb branch, which is another invariant of the theories, superconformal, field theories. So there is a classification, also rank 2 and rank 3, but let me say a few words about rank 1. And these studies studied based on the study of the corresponding Coulomb branch. All right. And in fact, L-2 of G2 and L-2 on B3 are in these stories, appears in these stories. So, and one, so it's even more precise, one particularly interesting class inside this, in this context, is a class of Argyres-Douglas theory. So maybe I should say some name. So Lee, so Bohan Lee, Xi, and Yan, sorry. In fact, classified all rank 1 Argyres-Douglas theory. Okay. And so this give and also sorry, and also they give the corresponding VOAs plus conjecturally each branch. So here, I'm not sure how much they are based on the computation as associated varieties, but I think it's a physical computation. So conjecturally, it corresponds to the associated varieties of the corresponding VOA. And now I can say the point, some are particularly, so this is particularly exotic. And what I want to say is that these are pairs in this context. Are pairs. But as I said, this one, in fact, appear also in classes, which is another remarkable class in this setting. So this means that so because of other works of another group of people I want to mention, the representation theory of these vertex algebras should be related to the column branch. So let me say another thing. So the representation theory of this vertex algebra should be related to the Coulomb branch of this, I don't know how to say, the source for the superconformal field theories. And this is based on the work of Shan, Peng Shan, Si, and Yan. All right. So let me say something a little bit remark, which is I find very nice. So let me put this here. Yeah. Is it okay for, so to summarize, this appears in this context, but in fact, more precisely, an interesting remark from the work of Li, Si, and Yan. So there is not only this vertex algebra, there is really a series or sequence of VOAs, rank 1. So if I say the series, I would like to say something of rank 1 Argyglass-Douglas theories, which give the corresponding VOA given as follows for. So here in my notation, this is the image of such theories. And what is G? So G is part of this series, which is an exceptional series, but different from the Deligne exceptional series, slightly different. So you have G2, B3. So this is the embedding we have seen before. You have F4, and you have all other exceptional. All right. And what is K? K. So this is J, G, and K is minus the Coxeter number minus 1. Not the dual Coxeter number, the Coxeter number. So what is this for the series we are interested in? So here it's precisely minus 2. I remind you that here H is 6 and HH is 4. Here it's also minus 2. And here it's also minus 2. So you recognize our vertex algebras in this series. But you see, there are others. For instance, let's focus on F4 and E6. E6, what is a Dynkin diagram? And here you know that the automorphism group of the Dynkin diagram is automorphism Dynkin. Dynkin diagram. So you know it's also Z over 2Z, something like that. And we know that the invariant part is F4. So in fact, here there is another series. So what is the level here? It's minus 3. In fact, HH for F4 is 12. H, sorry, for F4 is 12. And here it's also -3. Okay. And in fact, each time it's simply laced, it coincides with the exceptional theories with the level I will mention after. So this is also very interesting, and similarly to before. Okay, I want to comment something. So this is exactly a rank 1 Argyres-Douglas theory. So maybe if some of you heard, this is different from the Deligne exceptional series, which is exactly similar. So it's not exactly the same. You have this, you have D4, F4. So you don't have a B3, for instance. And what is K here is minus H over 6 minus 1. So of course, for the simply laced case, it coincides. But here for F4 and G2, it is different. Okay. And here what we computed with Arakawa is that with K and G like this, is that the associated variety is a minimal one for this series. Is it okay, Flor?
Yes, thanks.
Yeah. So let me just comment about F4 and E6. Now, similarly to what's happened with the previous embeddings, you have this, so you have a projection, and it is known from recent work of Juto and so on, that in fact, well, let's call it P again, the image of the minimal one is in the Bala-Carter classification is the unique nilpotent orbit of dimension 22 in F4. Okay, so this is a recent work of Fu, Juto, Levy, and Sommers. So this is known, and so maybe I want to formulate one conjecture, is that probably, according to all these stories and physical remark, we can expect that the associated variety of this should be this. Okay. And of course, I didn't say, but our result, I would like to say something. Our result about the associated varieties here, maybe I should say that this was conjecture. Oops. By Justine Fasquelle, using OPEs of the corresponding W algebras. But also it agrees, of course, with the physical predictions. Okay, so sorry, I am a bit long. So I wanted to say but now I would like to connect with some mathematical conjecture and say a few words about the proof. Sorry, I'm sorry for the length. Okay, so connection with mathematical conjecture.
Maybe, Anne, one question. Sorry, do you already have a conformal embedding between those two pieces?
That's a very good question. Between F4 and E6. Yeah. This is a very good question. I don't know.
Gotcha.
So indeed, first of all, we should first know whether there is something and whether it's conformal.
Yeah. Thanks.
Yeah, we don't know. And here we don't know how to adapt what we did. Yeah, it's not clear at all. It's quite reasonable to expect this, but so let me state several conjecture, and then you will see that our examples fit the conjecture. So first of all, conjecture. Yeah, so maybe I start with this because I explained many examples like this. We have orbifold. So in our example, in our example, we have something like that. In fact, the associated variety of the orbifold is the orbifold of the associated variety in our examples, including the expecting example with F4. But not true in general, certainly not. Yeah, I don't think it can be true. But however, we have a result of Miyamoto, which says something a bit weaker, but very nice. So assume that V is Lie. So I already say this is just a point. And conformal vertex algebras. And G is a finite solvable subgroup of the group of automorphism of your vertex algebra. Then the result of Miyamoto says that the orbifold vertex algebra is also Lie. Okay, so this is nice, but it's not our setting because we are not Lie. But one can expect, so sorry, this is a theorem. So we can expect similar statement for quasi-Lie conjecture. So this was suggested to me by Adamovich. So I don't know whether he wants I put his name, but let's say suggested. So similar. So replace you keep everything, but with quasi-Lie instead of Lie. And quasi-Lie mean XV has finitely many symplectic leaves, which is the case of our example because they are contained in the nilpotent code. And so all previous examples support this conjecture. Okay. Of course, there is another conjecture that I don't write down, that with quasi-Lie, we expect that the associated variety is irreducible, and this, of course, support. We always have nilpotent orbit closure. Slightly more interesting conjecture, not more interesting, but a bit subtler. This is related to the fact that we have finite extension. So I would like to say another conjecture. Is a question about that? No. Okay. So another conjecture is the following. Assume, so this is a conjecture formulated in our paper with Arakawa, Van Ekeren, and myself about collapsing level, but in fact it's related to this setting. Assume that W is a finite extension of a vertex algebra V. So this means that you have a conformal embedding plus finite extension. So as V module, V has only finitely many V modules. And then, so this induces, so you have an embedding like that, and then this induces Poisson algebra morphism between the corresponding ZU-C2 algebra. And then you have a corresponding map from the, if you take the covariant morphism, you have a map at the level of associated variety. And the conjecture is that then pi is dominant. So in particular, in our case, it's correct because it is of the same dimension. So all of our examples support this conjecture. So in particular, in fact, the morphism I explain, if you restrict to the minimal orbit closure, and similarly with G2, all these as example. And conjecturally, Z1 of F4 are an example. Okay, so this is another conjecture and a new example. In the setting of conformal embeddings, we had many examples, but always at admissible level. Here, it's not admissible. Okay, so sorry, I don't have so much time, so I say just a few words about the proof. Is it okay? Sorry, I was too long. So
This is great. Thanks. Yeah.
So just a few ideas of the proof and one more result. So in fact, it decomposes in several steps. So the first ingredient is obtaining a singular vector for G2. And here, contrary, as I said, contrary to before and D4, hard. Here it's hard. So the proof is nice, but what I want to say is that V is an element here, so V singular, of conformal weight 6. So just for information, for D4 and B3, we found singular vector of conformal weight 2. And here there is, I forgot to note, but I think there is something like 385 terms. But this was possible to do. Once you know the conformal weight, it's possible to search, but I have to say it's very nice work of Dai and Bohan Lee. And once they found the conformal weight, they did a big step, and then it was possible to exhibit a potential candidate and then check. And as you probably know, if you try to do such problems, once you have a singular vector, it's very beautiful, because then you can consider a subquotient. Oh, sorry, so at level -2. So you take this. So for the moment, I don't claim it is simple, but one can study the representation theory of this one using Zhu's correspondence, essentially. Because you know that the Zhu's correspondence it will be related to the projection in the Zhu's algebra. And plus, maybe I don't have time to detect, but you can use the notion of characteristic varieties. And as I mentioned, this allows you to detect all possible weights. And third step, you have to show that this is in fact simple. So in other words, it is what you want, and so you get the result for the representation theory part. So this is for G2. Let me say just one thing. For B3, it's not exactly the same. So it's too bad I don't have time to explain, but here the simple quotient is essentially generated by the image of the singular vector in B3 through all the story of embedding, and another one. So it's slightly more difficult. So we have the notion of sub-singular vector to study the representation theory. But what is beautiful is that we use the singular vector in G2 to construct not a singular vector in B3, but some element which is in the maximal ideas. And the last very important ingredient about associated variety, we use, oh, sorry. So I don't have time to explain. It's 1 hour, right? Yeah. So we use the W algebras associated with G2 and the subregular elements. So So I'm sorry that I don't have time to explain, but I remind you that this is a Drinfeld-Sokolov reduction associated with G2 and subreg. And what I want to say is that from the work of Justin Pascal, who explicitly computed OPEs, we know that the simple quotient, so this is a simple quotient, is in fact just C, all right? But the problem is that we cannot say something about associated variety because we know only for the Drinfeld-Sokolov reduction, but key point, in fact, the Drinfeld-Sokolov reduction of the simple quotient coincide with this. And which is C. So from this, using the work of Arakawa about associated variety, we deduce that these contain the subregular, plus the fact that this is C, it implies that the equality. You have no choice because, well, okay, I don't have time to explain, but the end of the argument is purely geometrical. But the beautiful thing is that we have this OPE plus the isomorphism there. Okay, so yeah, I think I stop. I already next time. Sorry for that.
This is great. Thank you so much, Anne. If you have any questions for Anne, please feel free to unmute yourself and ask. And I have a question. That's why I'm waiting patiently. Did you describe the Jou algebra? Oh, let me stop the recording so that people are more prone to asking questions.
Mm-hmm.
I'm just